I'm Alan Thorpe.
And I'm David Rogers, and together we host the Weather Pod.
In this special series on artificial intelligence, we invite leading experts to reveal how AI is being used across all sectors of the global weather enterprise.
We want to find out how business, the public sector and academia are using AI. Can it help improve the accuracy and quality of weather and climate information?
Can it help to make weather and climate information more useful and usable across a range of critical activities that are impacted by weather and climate?
There are many claims being made about AI, but what is its real value when it comes to helping business and society meet the growing climate challenge?
In this episode of the Weather Pod, David and I open a new series of discussions which focus specifically on the use of artificial intelligence, AI, in the weather enterprise. In this first discussion, we invite Professor Kirstine Dale of the UK Met Office into the studio. Kirstine is the Met Office's Chief AI Officer and is a Principal Fellow for Data Science. As Chief AI Officer, she is charged with embedding AI in the Met Office's core business, and she's initially focused on the use of AI in weather forecasting through leadership of the AI for Numerical Weather Prediction program. As Principal Fellow, Kirstine plays a leading role in shaping the future of data science, which includes artificial intelligence and machine learning in the Met Office's work. Kirstine is also the co-director of the natural environment theme of the Turing Research and Innovation Cluster on Digital Twins, and she is an Honorary Professor at the University of Exeter. Kirstine, welcome to the Weather Pod.
Yes, welcome, Kirstine.
Oh, thank you. It's great to join you both, and thank you very much for inviting me.
I wanted to start by really filling in some background. I don't know if others feel the same, but this area of artificial intelligence seems to have a whole plethora of words associated with it, which sometimes are used interchangeably. And I wonder if we could start by perhaps you giving us a thumbnail sketch of one or two of these. I'm thinking of things like generative artificial intelligence, large language models, deep learning, machine learning, and data science. I know we can't discuss the depth of all of those, but how do you see the distinction between some of those?
Okay, so if I start at the top level, data science is the umbrella term, and it's a multidisciplinary field that uses scientific methods, including maths, statistics, computer science, along with domain expertise. So in our case, that's weather and climate modeling, to extract meaning and value from typically very large data sets, so from big data. It's definitely not new. Data science has been around for a long time, and it's part of our daily lives. So, for example, when you wake up in the morning and turn on your smartphone using Face ID, that's data science. When you check on Siri or Alexa for the weather forecast, which don't do that, go to the Met Office's app instead. But that would be data science too. Google Maps, finding your quickest route to work, that's data science. So it's everywhere. It's in our daily lives. At the next level down from data science would be artificial intelligence. So artificial intelligence is primarily concerned with techniques that learn to mimic human behavior or intelligence. So, for example, machines or computers being able to understand language, so using natural language processing, so that's called NLP. NLP enables computers to understand text or spoken words. So, for example, NLP is a type of artificial intelligence, and that's used in ChatGPT that I'm sure both of you and many of your listeners will have used. Within AI, there are two main camps of artificial intelligence. First, there's narrow or weak AI, and that focuses on one problem. So, for example, Google Maps can tell you the route to work, but it can't tell you the weather forecast. Or the Met Office's weather app can tell you the weather forecast, but it doesn't tell you what to watch on television that evening. So that's narrow AI. And then there's general AI, which is much broader, and the goal here is that general purpose AI would have the ability to answer any intellectual task that a human could. I don't have any examples of general AI at the moment, but that's a real area of focus for the big tech companies at the moment, trying to pursue the goal of general AI. And then generative AI, that's something a little bit different. Generative AI is where AI uses models, uses data to create new content. So, for example, ChatGPT or a chatbot, that's generative AI, or DALL-E, which is the drawing model. So you describe what you would like it to draw, and then it creates a picture for you. That's generative AI. So that's data science and AI. And then the next term to explain is machine learning. So machine learning comprises a large range of techniques and algorithms that allow machines to learn. So whereas AI is the destination, machine learning is the tool. And then what next? Deep learning. Deep learning is a subfield that focuses on things like neural networks and looks at different modeling approaches to deliver artificial intelligence. And then a large language model is a type of generative AI that's specifically designed to generate text-based content. So that covers some of the basic terms.
Do you think, Kirsten, that if you like, the public discourse in the media, etc., is very informed about some of these differences, because they're quite fundamental, aren't they? Really, the way you've described it.
Well, they are, and I think that sometimes there's a temptation to use the next term up in terms of the umbrella, and it infers something that's not quite right. So, for example, at the Met Office, we do say that we're using artificial intelligence, but mostly what we're using is machine learning. So mostly what we're doing is thinking about machine learning algorithms. But it does get described as AI. I think in the future we'll be using a lot more AI, and certainly as there are some areas of the office where we're looking at Office 365 Copilot and other enabling tools like that. Now that is very definitely artificial intelligence, but the work that we're doing on using machine learning for weather forecasting is probably more accurately ML than it is AI right now. In the future, it could be different, but right now it's ML.
So that kind of neatly goes into this kind of issue about what do we actually do as meteorologists. So, for many decades, we've used statistical methods to remove systematic biases in numerical weather prediction and basically post-processing. And the new, I really guess you mean machine learning methods, are a kind of evolution from this approach. And are they really something completely different, or are they how would you describe the difference between the way we went about statistical methods versus what we're doing now?
Okay. Well, I think what's probably worth saying is, just as I said at the beginning, that data science is part of our daily lives. The Met Office has always been a data science organisation in that it produces, stores, analyzes, visualizes, and extracts meaning from vast quantities of data. At the Met Office, big data is our every day. We've got 215 billion observations coming through every day. We've got 3 million lines of code. We produce 18 terabytes of data a day, which is the equivalent of something like 27,000 CDs. So we have been using data science for a very long time. And when I mentioned machine learning's also been something that's been happening at the Met Office for a very long time, but we probably haven't called it machine learning or AI. So, for example, clustering is used for cloud classification. Gaussian processes have been used for downscaling climate prediction. So this is familiar territory for us. It's just the next step in the journey. And I think What is different is the rate of change that we're experiencing at the moment, and that is being brought about by an explosion in the amount of data that's available, acceleration in the development of more sophisticated techniques that enable us to, data science techniques that enable us to extract information from the data, and enhanced availability of high performance computers. So once you've got the compute and the availability of the data, and you have these sophisticated tools, then you can move more fastly. And I personally think that actually data science and machine learning and AI is just the next step in our stats journey, and it's been brought about by what is sometimes called the AI revolution. So this explosion of data, more compute, and increasingly sophisticated tools. But I guess it's a question of scale and sophistication, because we now have this compute and data and more sophisticated algorithms. We can move faster in terms of developing the approaches.
So basically an evolution rather than a revolution to a large extent. Just to kind of elaborate on this a little bit, because it's interesting that we have in our business, basically, as you've said, we've dealt with large data for a very long time, and a lot of those others who are coming to the marketplace are the ones who have suddenly discovering big data. So we've had tools, and therefore it is more of an evolution than a revolution. Yet in other fields, it probably is a revolution rather than an evolution, because they weren't there in the first place.
I think yes. I think we're ideally placed to embrace this opportunity.
And in a certain sense, you could argue that meteorology has been ahead of the curve for a long time, because it's been a long time since we've had big data. We've had compute power. We've analysed data, very complex data sets. So in a certain sense, perhaps we underplay the fact that the weather enterprise is, in a sense, can be thought of as one of the forefront areas. Or am I overplaying that, Kirstine?
No, I really like that. I think that we are not only ahead of the game in that we have always been this big data organization, and that we have some of these tools in place. We have experienced a lot of these challenges are familiar to us, but I think we're ideally placed to embrace the technology more fully now.
You're listening to WeatherPod with Alan Thorpe and David Rogers.
Yeah, let's move on. I mean, I think one of the areas that's particularly attracted a lot of interest is the use of these techniques, say deep learning or machine learning, to actually predict the weather. And we'll come on to that, I think, in a minute or two in our discussion. But before we get there, I wondered if you could just comment a bit about other applications that you see for AI and deep learning, because I think it's not just about the prediction, which is important, of course, the weather prediction itself, but how is it being used more widely? Give us one or two examples, perhaps, would be great.
Okay, so as you say, we're using machine learning to look at weather forecasting, but long before that we were already looking at how to use different machine learning techniques across the whole of the forecast production chain. So for example, if you think about it as a chain, on one side you have observations, and then on the other side you have products and services. So if I just give a couple of examples running along the whole chain. So on the obs side, so observations, we've been using machine learning to classify ocean temperature probes. So ocean temperature probes, so expendable bathyothermographs, are used to record the temperature, but the metadata for I think it's nearly 50% of those ocean probes is missing. And if you don't have that metadata, so you don't know the type of probe, then you can't do the bias correction on it. So we've been using machine learning to infill some of that missing data, and that's enabled us to do the bias correction. So moving down the chain, so an example from simulation. We've been using machine learning at the Met Office to identify sudden ionospheric disturbances in the data from the new lightning detection system, Lila. And in sometimes those changes that we can pick up using machine learning in the SIDS data, they indicate a solar event or a coronal mass ejection. So that's really important, and it's such an enormous data set that having machine learning do that for you really speeds things up. And then moving towards the right-hand side of the production chain, so thinking about when it's actually getting to sort of hazards and impacts. We've been doing a project with the National Met Service in South Africa, developing future wave climatologies, and that's really important in South Africa because they get monster waves and they have a lot of critical national infrastructure. But if we can use machine learning to generate future climatologies for the waves, then they have a head start on making sure that their infrastructure is resilient to any future changes. That's really important. And then we also have been using a range of discovery and correlation methods to select climate indices that predict temperature and precipitation over northeastern China, and that's strongly linked to maize production, so food security issues. And we've developed it in this area of China, but the technology can be used in other areas of the world as well. So we're now starting to explore where else could you use this to look at food security issues. So it's used right along the whole value chain, and it's being used at the moment to explore ways that we can take model output and personalize it. So I know, for example, that you on one of your other podcasts you've spoken to my colleague Paul Davies. He talks quite a lot about the desire to move from hazards through to impacts and think about personalizing forecasts. Well, that's exactly the sort of problem that machine learning can help us with. So AI, machine learning, data science is not a new tool, but I'd say it's increasingly one that we're turning to for complex problems that we need to tackle at scale.
So before we just jump into more details about prediction, I wanted to pick up on what you said about observations, and you apply the application to oceanography. But I was wondering about the utility just for standard surface observations. Well, around the world there are a lot of observations that lack metadata, and therefore they're pretty useless. And there's been, we have a number of cases where we've seen attempts to use these data. They would be very valuable in terms of verification and potentially into assimilation, but they're not because they really lack metadata. Do you see the tool being applicable in for those sorts of situations?
Definitely. I'm really glad you mentioned it, actually. I think that there's a real opportunity for us to use some machine learning techniques to infill missing data, and that's going to be particularly important in some data sparse areas of the world.
As I can see, there's immediate application, collaborative probably opportunities in areas where we're all. There are a lot of efforts to enhance observations. Make better measurements, or more measurements. But there's also a real need to fill in the gaps where you really are not going to be making many new measurements, but you do need more information, and we haven't got the techniques applied in those places. So that will be very interesting. But I'd like to come on to the weather prediction problem, because this is of course something that probably gets a lot of people very excited. What's really the basic idea behind using neural networks for weather prediction, and how does it work in practice?
Right, that's quite a big question. I think I'll step back a little bit first. Over the last, I reckon it's probably about 18 months to 2 years, we've seen really significant progress in the use of machine learning approaches to forecast the weather. And this, there's been a series of academic papers that have charted the rise of machine learning, data-driven approaches. And just to give you a couple of examples, these are nearly all published by big tech organizations. So, for example, in the last 18 months, months, NVIDIA have published a paper on ForecastNet, which is their model that uses Fourier transformers. Huawei have published the Pangu weather paper that uses vision transformers, and Google DeepMind have published a GraphCast that uses graph neural networks. So we're seeing over the last 2 years, we've seen a real acceleration in different, primarily big tech organizations using machine learning to forecast the weather. And it seems not only is it getting faster, but it seems to be getting better. So this has caused us at the Met Office to pull together some of the activities that we already had in place and create a new program called AI for Numerical Weather Prediction, so AI for NWP. And as part of that, we have a project where we are trying to build the Met Office's in-house capability to develop a machine learning model for weather forecasting. And we could have chosen a variety of different approaches that the big tech organizations have been using, but we've chosen to use graph neural nets. And we've chosen this approach. So this is the same approach as Google DeepMind. We've chosen this approach because graph neural nets have been shown to scale well, to be really effective and capable of handling the multi-resolution inputs, the complex data that you need to produce a weather forecast, and they learn well as well. So they've been shown to be ideally suited. So I'm also conscious that I didn't really cover neural nets at the beginning when we talked about different terms. So a neural net is it's a model designed to mimic the function and the structure of the human brain. It's a network of interconnected nodes that can communicate with one another, just like neurons in the brain. And they're known to be that they're very adaptive and they can modify themselves, so that they are absolutely perfect for the challenge of weather forecasting. And graph neural nets can map onto a graph and can be represented as a graph. So perfect when you think about how we forecast the weather.
You're listening to WeatherPod with Alan Thorpe and David Rogers.
So to pick up, Kirsten, on that, give us an idea of how it's actually done. I mean, in a sense, all we have is information from observations about the state of the atmosphere. That's our input ingredient, if you like, from the real world. And numerical weather prediction fills in the gaps using data assimilation, and then we have a laws of physics model to predict the weather. So how is this GraphCast method, how does it diverge from that approach? Where does it diverge exactly?
I'm not too sure I'd call it diverging, as complementing, and in some cases it's very, very similar approach, really. If you think about the graph neural network being a network of nodes, well, that's very similar to the weather at different locations, and the nodes can communicate with them. So in much the same way as the weather in one area will affect the weather in another area, the node structure of a graph neural net mimics that as well. And not only that, but the graph neural net can learn and adapt, and that's exactly what happens, what we need with weather forecasting as well.
But just to be devil's advocate for a moment, we don't really observe that much of the weather in the sense we have imperfect measurements every day. And one of the big advances in numerical weather prediction has been the ability to fill in the gaps through data assimilation, using actually a numerical weather prediction model, a physics-based model. So I wonder how does the deep learning, machine learning approach deal with that problem? Because there's not really enough observations, certainly in the past, to really act as a teaching data set or a learning data set, is there?
Well, I think it's probably worth noting up front that machine learning approaches are not an alternative to numerical weather prediction, that you need numerical weather prediction to provide the training data sets and to verify the machine learning model and to initialize it. So you would always need these two approaches.
Okay.
That's interesting, because I think sometimes that notion gets lost. It's like, we will replace you. and
those
I think
papers that have been published, you mentioned, Kirsten, if you read them, they definitely read that way.
Yeah.
That's not
Maybe
how I read them. So I went to a talk quite recently by some of the big tech organizations, and they were at pains to say that they don't see the end of numerical weather prediction anytime soon. And I agree with that. I think these are two approaches to forecasting the weather that are going to need one another to move forward. Maybe in the distant future there wouldn't be a need for NWP, but I certainly can't see that stage at the moment.
Going back to the sort of practicality, so how would you use the two if in an operational setting? What does it look like from a forecaster's point of view?
Well, from a forecaster's point of view, I hope that it would probably seem seamless to them. It would be nice to think that in the future we would be able to select whichever approach, whether it's machine learning or whether it's a purely NWP approach, we would be able to select that for that particular forecast. So if that's the most appropriate route to take, that our operational forecaster wouldn't even know that we're using the machine learning one, that it would just slot in. But sorry, I've not done very well answering that one.
I mean, one of the big claims that I've read about is that this use of machine learning for the prediction of weather is very fast. So we can they say they can produce a prediction within minutes, rather than what it takes us now with a supercomputer to produce a weather prediction, maybe let's say of order an hour. Seems to be that it's speeded things up. Is that a fair comment, a fair summary?
Yeah, that's one of the really big advantages of the machine learning approach. It's been shown to be tens of thousands of times faster and use tens of thousands of times less compute, so less CO2 burden as well. And additionally, they're becoming more accurate. Now, I don't see that as a threat. I see that as a massive opportunity for us, because that means that compute that might have been necessary to run NWP is now going to be available, so we get to say run a larger ensemble size, or to think a bit more about how we move from hazard to impact. Or there's a world of possibilities that this opens up for us, because the computational heavy part of NWP might not be necessary in the future.
Okay. Before we move on out, I'm just going to ask a further follow-on on this. I mean, one of the, I guess if you look back in the history of the weather enterprise, there's been a very close coupling between the development of our understanding, our knowledge about the way the atmosphere and the oceans work, using, basically using physics to figure that out. And that's not a journey that's come to fruition fully yet. We know a lot, but there's an awful lot we don't know. And I suppose one of the things that some of us worry about is that the sort of development of new science maybe slowed down because actually, in a sense, it's seen that machine learning can do the forecast quicker, doesn't need necessarily these large NWP models to do that. And therefore, there's not so much funding and pressure and interest in developing the physics knowledge about the atmosphere, oceans, and land surface. How do you feel about that, which is slightly pessimistic outlook, but just wonder how you felt about that, because I think some people worry about that as a risk.
I don't worry about this so much because I think that we need to understand what's happening, and that requires physics. So we have techniques like explainable AI, but I think it's really important that weather forecasting isn't a black box, and in order to prevent it being a black box, we must have an understanding of the physics that's going on. This is why I think that the future isn't a machine learning approach, or just like I don't think it's a purely NWP approach. I think the future is a hybrid, which brings together these two approaches so that we can have the speed and the low computational cost of a machine learning approach, but we can also have the understanding, and with that comes the trust that an NWP model would deliver.
We've sort of, you've gone on to discuss the future, and I wanted to just continue that a little bit. I mean, all of this seems very, very new, particularly to some of us who have been working in the field for a number of years. How do you see this going into the slightly longer term future? Do you see any big changes to the way the weather enterprise will have to operate, or what are the opportunities perhaps that might come to fruition over the next, say, decade?
So I definitely see a lot of opportunities for us. I think that if we can run models faster and more cheaply, then this enables us to look at other opportunities. So like I said, to move from hazards through to impact, to make forecasts more personal. So for example, I'm a sailor. It would be really nice if instead of having a look at getting a forecast and having to figure out whether it's a good day for sailing, it'd be nice if there was a forecast that was created just for me that said try and get out of work early today. I think that there's a range of these sorts of possibilities that will open up. For example, let's think about running a greater ensemble size, so to communicate better about the uncertainty behind our forecasts. This will become possible because the computational cost will be less. And when I talk about this, I'm mindful that I don't think this is 10 years hence. This might only be a few years hence. Data science is moving so fast. I think those horizons are a lot closer than we think. Do I think there will be big changes in the landscape of operational forecasting and how national Met services work together? Possibly. It's hard to imagine how this really transformative technology would take hold in our sector without it necessitating some changes. So yes, but I think that these changes will be good if we can make sure that we're working collaboratively to identify what's the desired outcome, what's the best possible solution, and use our combined resources to try and deliver that.
You're listening to WeatherPod with Alan Thorpe and David Rogers.
I pick up on the, I mean, it's probably a topic for a complete other weather pod, but on the application to impacts and we, I mean, with Paul and others, we've been talking about how to build a better digital multi-hazard early warning system. And then obviously an integral component of that is the inputs that come from the weather end of it, the production sort of side in terms of identification of hazards. And then, as you've said, it's the really interesting and important issue that we have to embrace is how do we deal with this from an impact point of view, and how do we build in the human dimensions. And one of the things we've been talking about is how do you really want to use machine learning, AI kind of techniques to build agents to understand the people that you're impacting or that will be impacted by the events, and you want to bring in behavioral science and all sorts of other things into that. So there is a very interesting opportunity at that end of this business to see how that could be done quite seamlessly, I think, if I follow what you're saying, from the forecast all the way through to the use of the similar kinds of tools that will actually make for personalized information, which ultimately is essential if we want people to take effective anticipatory action. So I think there's a fantastic opportunity there. And because of its relatively lightweight in terms of computational requirements, it's potentially available to everyone. And I think one of the things I want to bring this question to you about we wanted to sort of, there's a lot more interest at the moment, or a lot more engagement with the private sector in developing these tools. And you mentioned this, but you also mentioned the Met Office is really advancing its own capabilities, and clearly, so there's quite a lot of balance there between what the private sector is doing and what the public sector, and clearly opportunities for collaboration as well as sort of the usual competition. What I'm particularly curious about is, where does the National Weather Service of a developing country enter the picture? How can they participate? What should they be thinking about in terms of engagement? Should they worry more about an end use of the information, or should they really be engaged in really trying to understand machine learning and applying it to their own observational data sets, and so on? Where would you see a much less well-equipped organization than the Met Office play in this space?
So I'm not sure I can answer that question, but I can say that this is being looked at quite closely at the moment, and there's several groupings of national Met services that they're coming together to look at what this might mean. Machine learning has the potential to democratize weather forecasting, because it removes the barrier to entry of needing a high performance computer. So that's quite a significant change. And I don't think that we've fully worked through what that might mean for how different Met services embrace the new technology moving forward. But it's certainly a hot topic. So I guess this one is an unresolved question at the moment, but it's certainly getting a lot of attention.
Just to pick, you've said a few times now, Kirstine, that we don't need, or these techniques mean that we don't have such a great need for computing capability, supercomputing. That sort of worries me a little bit, because I find it kind of intuitively not obvious that we don't need, at some point in this hybrid way of doing weather prediction, we must need to use serious computing power to be able to generate, if you like, the data sets that the deep learning uses. And so, because otherwise I fear that one could conclude that we don't need supercomputers, that Met services in developing countries, or even, dare I say it, in the UK, all they need is a laptop, and away they go.
To be really clear on this one, I'm not saying that you don't need supercomputing capability. I'm saying that it changes the operating model for how you might use that. So, for example, I don't foresee that we'll hit a point where we don't need numerical weather prediction, and you need to have the compute capability to do that. And I think that even though the machine learning models might be faster and use less compute, it's not that we won't use the compute for something else. I think the opportunity, the really exciting opportunity exists is how might you use the fact that you're spending less on the machine learning model to improve the forecast. So increase your ensemble size, move from hazards through to impacts. So it's not really that there's less supercomputing needed in the UK, for example.
If I took an example specifically to say to a part of the world where we do a lot of work with the World Bank in South Asia, so we have a regional program in which there is the model output is being shared amongst all countries, but it's essentially being used so it's available regionally and then it's shared. So in that model, and if I follow what you're saying, you could take the machine learning aspects of it and really apply that nationally. Even you're still using numerical prediction, but you're not every country needs to do that on its own. It can do its own kind of machine learning aspects, AI aspects of that to utilize the available output that is shared amongst all the countries in the region. And does that work? Is that how you might imagine it? Or I mean, it's quite a different picture from an institution like the Met Office, which can do both. But if you had to choose, and you said, well, I have a small country, rather than really invest in high-end computing and run models, I can use the model outputs that are available and then utilize machine learning to actually apply that knowledge in a more effective way. Would that work?
I think it's a really interesting question. I don't really have a good answer to this other than to say this is being looked at. This is exactly the sort of thing that's being considered at the moment. What might the changes in approach to weather forecasting mean for national Met services and for the whole global endeavour? I can't. Sorry, David, I don't know the answer to this one.
But it's interesting, as you say, it's being looked at. So, I mean, and presumably then the idea that there are less modelling centres, but there are a few, something that Alan and I have talked about for many years. You don't need too many of them, but you need some, and you need some diversity. But then it means that, as you said, democratising the use of that information means that people have the tools that they can then exploit that more effectively, perhaps the model outputs more effectively by using AI in that way. And then,
for a small country Met service, one example of change there would be that perhaps today they're quite interested in running limited area or regional models for their area based on boundary conditions from global models. Instead of that, perhaps in the future they don't need to do that. They can just use machine learning to downscale what's there from the global predictions that are available from the centres that are able to do that. So it kind of shifts their focus of attention from, in a sense, mimicking the traditional NWP approach to their area, and instead figure out, and their expertise would change a little bit, figure out how to use statistically and with data science techniques to downscale to their country.
So I often hear AI talked about as a transformative technology, and even within our sector, I hear about AI bringing a paradigm shift in weather forecasting, which sounds really dramatic. And I'm not sure I'm totally comfortable with that language, because I think that implies that, you're throwing the baby out with the bathwater, that we lose all of the experience and expertise and hard-won knowledge that we have in how to forecast the weather using physics. I don't believe that's going to happen. I believe the future is this hybrid approach. But part of me, a significant part of me, does believe that there is going to be a shift in the landscape of weather forecasting in the future. What that's going to look like, I don't know. It's being worked through at the moment, looking at the various options. But we're doing our best to stay agile and be able so that we can embrace and make the most of what this technology might mean for us. When I say us, I mean society. I'm not just talking about them.
Sure. I mean, one of the corollaries of what David said earlier is, and what you said actually, is a lot of these developments have been done in big tech companies in the private sector. And I was just wondering whether, therefore, there is an opportunity here for better partnerships between the National Met Services and those private sector companies. Now, of course, that's the positive gloss on it. The negative would be, why are those private sector companies actually doing any of this work in the first place? What do they see as the opportunity for them? But is that partnership model gonna help in the future, Kirstine?
Yeah, I definitely think so. So you'll recall at the beginning when I was describing what data science is, I said that it was maths and computer science and statistics coupled with domain knowledge. Well, I think this is a really good example of that in action. Big tech had the hardware and the data scientists needed to move first into this space. But if they want to continue the journey, then I think they need domain expertise. So not only is partnership desirable, I think it's absolutely essential if we're going to improve weather forecasting capabilities. And that's certainly something that I know UK Met Office, but also other national Met Services are looking across big tech organizations and other national Met Services to have a look at what are the partnerships that we need to move forward at scale.
Kirstine, I think we need to draw to a conclusion, and just want to really thank you for getting us started on our WeatherPod journey into the AI world. I know we've just scratched the surface in this podcast, and you probably feel a bit dissatisfied that we haven't been able to go in more depth in some of these areas, but we really hope we can do that in future episodes. But you've given us a really good overview of some of the really fascinating potential risks and opportunities of this field. So thank you very much.
Yeah, thanks, Kirstine. It's really been really interesting and insightful. I think there's a lot more questions we could be asking, but hopefully we'll return to those in future episodes.
Oh, thank you both very much for inviting me along. It's been a real pleasure having the opportunity to discuss this with you. Thank you.
Well, that concludes this special AI episode of the WeatherPod. We hope you've enjoyed it. We'll be back in the near future with another episode dedicated to how the global weather enterprise is using AI and related technologies. If you have any comments, then please contact us at support@gweforum.org. Goodbye for now.